tonight's homework, again, not a big set, just 46 through 51, and you should have time to work on that at the end of class if we process through this material efficiently. So the first thing that we need to do on our paper is create a 10 by 10 grid. And that's a weird name because some people call a 10 by 10 10 out and 10 up. When I talk about like a 10 by 10, I'm really meaning like negative 10 to positive 10, negative 10 to positive. So really it's like a 20 by 20, but it goes 10 every direction. So go 10. So don't put your center point at the top left of your paper. You want to put it more towards the middle. We're going to use one graph for multiple problems today. So please put this in the middle of your paper with plenty of space around it. Allow 10 each direction. Now on my screen, I don't think I quite got 10. I got like 9 or 8.5 or something like that, just because my screen is only a certain size. And then I will read while you guys are doing that. So remember that when an object is translated, rotated, or reflected, it does not change how. What doesn't change in a translation, rotation, or reflection? The size, right? The size of the shape does not change. Everything else could change. What way it points, how it looks, how it's flipped, if it's up or if it's down, quote unquote, all of those things could change. So for this reason, those types of translations are called what? What type of transformations are they?
Rigid.
Rigid, right? Rigid means doesn't change size. Rigid is also a tool company. In this lesson, we'll explore new transformations that do change how the object looks in regards to its size. So as we work today, ask yourselves these questions. What parts of the shape are changing and what parts stay the same?
Good morning. Caroline Whitstock, please come to the office. Caroline Whitstock, please come to the office. Thank you.
Now when we're making an XY coordinate grid, which a lot of people say this is a graph. Well, yes, it's a type of graph. But I want to get you guys like comfortable with the fact that this is what we call a coordinate grid. Because grid, obviously, grid made of boxes. But by coordinates, like you, and you may not know this, this is part of an episode of Black Mirror. Every time you take a picture with your camera phone, you know that coordinates are attached to that. The actual GPS location of where that picture was taken is attached to that. For the fact of if it somehow needs to be used later in like a where did this happen, what was going, like in an investigation type sense, they know exactly where it occurred. So realize that also on that whole digital danger side of things, like every time you snap a picture, send a text, or like coordinates are being logged in your records. Now those coordinates deal with what? If it's the yes, thank you, latitude and longitude coordinates, right? Which are a little bit weird because the Earth is a circle. Or sorry, a sphere, an oblong sphere if we want to be technical. Coordinates here are talking about what? We call this coordinate grids. What coordinates are we talking about?
X and Y.
X and Y. So please, anytime you make a coordinate grid, you want to label X and Y because that's not always what we're talking about. We will introduce a Z coordinate, which if you can imagine this, would be coming off of the paper. Now, when we draw that with a 3D coordinate grid, give me your attention for just a moment. So we have y-axis still, x-axis still.
Whoa, brother.
And the z-axis. The z-axis is coming out of the paper, right? We're not using that yet. But when we get into three-dimensional graphing, so you would go like 3 on the x, 2 on the y, but then if it's like 5 on the z, it might have to come back, like it changes in a third dimension direction. So all of that to say, please label your x and y when we make just the 2 coordinate grids. First objective, in A, place those points on your grid. I'm not going to do it first because I want to make sure we all can find those points accurately. Those points are ordered x, y. 2, 1, 3, 1, 5, 5, 2, 5. And then we can do this quietly on our own. Think through B, jot down a prediction, and then do C. Okay, so plot your points for A, For B, further down your paper, just put a little B like near the bottom of your paper. Predict, and I mean say when multiplying by 2, I think, da-da-da-da, and then try it. What kind of shape is this? Yeah, it's a trapezoid, right? Because it's got 2 parallel bases at the top and the bottom, but then the other 2 sides aren't. So this is a trapezoid. Now here's the reason you have colored pencils. I'm hoping nobody was like, if you already got to C, you didn't write a good answer for B. Like you need a complete sentence there, please. Use a different color when you go to do C. So don't use your pencil, and if you've already been using a colored pencil, use a different color. So when you go to plot those points after multiplying coordinates by 2, you are changing color to do that. Oh my god, I forgot I put it there. So, all of this is not helping. Whatever this is, which is mine, I don't know why that has that post-it on it. What do you do? I'm going to take this, but I'm assuming there's work for me to go with it. That's it? That you have to finish AO extensions. So, dude, this should have been your priority last week. Come on, you're not helping yourself. So, do you have AO today? Yeah. So, I'm going to leave this in our bin. I may not be back by first AO because I have a dentist appointment, but after I'm not very lunch, you come down to AO and move this back. You're not sitting with anybody else or working with anybody else. Grab this out of the bin and keep working, okay? When you leave AO, put it back in the bin. Do not take this with you. So yours is sticking out, so you can just grab it real easy. I don't think anybody else should be turning papers in. What's a prediction that we have here? Lizzie, what do you think is going to happen? What do you have for B?
I think the shape's going to get larger.
You think the shape is going to get larger. Gwendolyn, do you have any more specific words as opposed to just larger? Increase. Braden, what'd you say?
I said that one, it would increase maybe double.
Ooh.
Specifically.
Maybe double specifically.
And then it would also move diagonally upwards.
And it will shift diagonally upwards. A lot more details there. Connor, what'd you say, man?
It would like go up over and probably get bigger.
Go up over and probably get bigger. I like all of those descriptions you guys said. So I'm going to go in red to make it real obvious. 2, 1, when I dilate that, becomes 4, 2. 3, 1, when I dilate that or multiply by 2, becomes 6, 2. Be careful. The order is important, how we say it. 5, 5.
10, 10.
This is going to be the one that's tough for me. What? 3, 1, too far. Hold on. 2, 1 became 4, 2. 3, 1, 4, 5, 6, 2. Yeah, my bad. Good catch. 10, 10 Yeah, 10 is like off my screen. Oh, I can get to that one. I just can't really get to that. So it's like up here is my 10-10, but at that intersection. And then 5-2, or sorry, what is this point? 2-5, right? Not 5-2. 2-5 becomes 4-10. And then if we connect, my base is now 2. And we would go across the top. And we get still a trapezoid, but how does its size compare? Quinn?
Double the size.
Now what do you mean by double the size?
All the coordinates are doubled.
All of its coordinates are doubled. I agree with that. Each side is doubled. Check this out though. If I put my old trapezoid in the new one, does it look like I could only fit 2 of those in? Ah, I could fit more than 2. Be careful when you talk about doubling. Yes, the red shape has dimensions twice as big as the blue shape. But when we start talking area, it doesn't work that cleanly. Now, it's not tough. I'm debating whether to tell it to you now or not. I think I'm going to wait. I'm going to wait. We'll talk about what actually happens to the area. Now, you could make that prediction. Like, what if you had a square that was 2x2 compared to a square that's 4x4? How do those areas compare when we double? So think about that as we keep moving forward. Now, we saw last week when we played in those Desmos activities that when we flip over an axis, right, we actually kind of reflected first, I think, and then we derived the points. I'm getting ahead. Sorry, so formally, we should write down the definition in our notes that a dilation is a stretch or a compress. So all I really care that you have is that a dilation will stretch or compress from a certain point. And that last part is more important than you realize. And I got some people not writing right now. A dilation is a stretch or compress. What's proportionally mean here? Can one side double and the other side triple? No. So proportionally means like everything happens the same. Right? So it's stretched or compressed proportionally from a point called the point of dilation. Normally we actually call it the center of dilation. The point of dilation is kind of lame.
I get the point.
So the reason that in this image it looked like our shape moved diagonally was because our center was the origin. So you might want to pop back up to where you drew that in your notes and say that the origin was our center of dilation. And then we realized this last year. The word diameter is going to encourage you to put an A after the I here. Dilation does not have an A after the I. It's just D-I-L-A-T-I-O-N. Dilation. Cool? So dilation is a stretch or a compression. So if we look at 43 and we hypothesize these questions, I'll swap my screens. So we have a new shape, this triangle. And you don't have to do this, but you can. If you want to throw this on your graph, we can kind of determine where these points probably are. It looks like this is like -6, 8 probably. And we can derive all of these. -2, -4, probably 6, -4 looks like. So think through these questions, and here's what I want you to put on your paper. multiplying by 1/2 will blah. Multiplying by 1 will blah. Just real quick, 4 sentences. Now the third and fourth are going to be the tougher ones. What do you predict will happen if each coordinate multiplied by half, multiplied by 1, then multiplied by -1, multiplied by -2? Now you could use the shorthand notation. So if I was doing this, lazy Micah Hudson, 7th grade student, would probably say, what will happen if multiply, actually I can make this easier, multiply xy by 1/2, and then write my answer. Then, oh, ditto marks. Yeah, ditto marks. Make your life real easy. You don't have to rewrite multiply xy by. But then it changes. We do 1/2, 1, -1, and then -2. So make those predictions. Take a minute. And then if you want to test it out, if you get done with those predictions, go ahead and test it out. And you can use the original shape we drew. You don't have to use that triangle.
But the triangle is bigger, so I would use the triangle. Actually, no, if I try to use it with a triangle, it will probably go out of bounds. By out of bounds, I mean out.
Yeah, if you do -2 and you're using points of like 8, obviously we're going to end up with like some values bigger than 10. So Quinn, then the question would become, can you extend your graph to fit those on?
No.
It depends, right? It depends if it needs to extend out wide or extend tall, because if it needs to extend tall, you might be able to fit it.
You might be able to extend it down.
Make those predictions. What if we multiply by -1? What is that?
It just flips.
Shh. I need some sort of like really quick like button that's like a buzzer. That's like no. Well, yeah, but I need something that just when somebody's gonna blurt out an answer and we're not ready yet. So Simon, if we come over to you and ask, what's gonna happen if we multiply by 1/2? What do you think?
It's going to get smaller by a half.
Yeah, it's gonna get smaller by a half. So if we use one of those math words, we could say. What did they use in that definition of dilation? What was the fancy word? Compressed. So it's going to compress to half the original shape. And actually, depending on where, the new one might just end up inside the old one. If you tell it to do it from the origin point versus from a point on the corner. So imagine, what if we tell it from this point, cut everything down by half, the triangle will actually shrink towards that point. Now we're not there yet. You're going to do some experimenting with your practice and everything else. What about if we multiply by 1, Marin? What do you think? You gave me 2 answers. George, what do you think?
Well, I think it will stay the same.
All right, let's get some verification. Olivia? Except if I could spell nothing.
You know
Nothing!
You know nothing.
You know nothing.
So, multiplying by 1, now, to bring back up a technical word, that's the multiplicative, and I would actually like you to write this down. We call that in math the identity, because we get back what we start with. Multiplying by 1 is the multiplicative identity, right? Nothing changes. So what is the identity for addition? 0. What's the identity for division? Doesn't change, Brady. 1. Again, if we divide by 1, same as multiplying by 1, nothing changes. What? Now we're getting hard. Marley, what about if we multiply by -1 for each of our points? Turns it negative, okay. I don't know what that means about what it looks like, though. Micah?
I'm guessing that it'll flip across the graph.
Flip across the graph, okay. Savannah, hope you're recovering well. Quinn? What do you think? Multiply by -1.
You would flip it, like, or
Flip it out.
you would, so the way I wrote it was -x, -y.
Okay, so this becomes -x, -y. So, like, if it was like 2, 3, it becomes -2, -3.
So I actually graphed it.
Braylon actually graphed it.
So basically, it's like, I don't know which, wait, so it's like the one top left, like the first quadrant?
So this is actually horrible. I disagree with how we did this. Because positive rotation goes that way, if we start in quadrant 1, you positively rotate into quadrant 2. So if you're talking top left, you're actually talking quadrant 2.
Okay, so basically like flips, diagonally,
Diagonally.
So it flips from 2 to 4. Yeah.
Flips diagonally, or if we want to be technical, it reflects. Do you know what line?
The origin point.
Hmm? It reflects the line y equals x, which is this line, except it goes through the origin. So if you do this line through the origin, and you can reflect any line you want, but if we reflect that line, a triangle that over here looks like this, over here will look like that. Instead of it points towards the origin here. It still points towards the origin, but now instead of pointing down right, it's pointing up left. So if A was here, A would become here. If B was up here, B comes down here. And if C was out there, C would be out here. Kind of crazy.
So
Actually, no, I lied. I flipped B and C in the wrong places. C should be down here, B should be here. And if you try it out, you'll find proof of that. Sorry, I was moving too quick. So imagine flipping across this line, that being your mirror. C has to come to the line, through the line. So C actually ends up down here. Sorry, turned it in my head.
No, what if you have a shape that's like symmetrical from inside the origin, like a box inside the origin, but you flip it diagonal.
We will do situations like that. So just hang on to that question. We will get there. And then multiply by -2. Gabe, this is coming to you.
So basically, was like the number gets like dilated by 2, and then it reflects.
Yeah, so we still, and please jot these down because this will be in your homework. I forget if it's tonight or not. We have a reflection across that line, x equals y or y equals x. Whichever way you write it, doesn't matter. It is that diagonal line. And then, dilate with a scale factor of 2. And it's just an and. Really, it's a substitution for an ampersand. But if I was trying to do, no, yes, maybe.
I think
backwards.
that's good.
Oh no, it's not.
No, that's good.
I get confused between the treble clef and the ampersand. Because there's treble clef. So reflect X, Y, and dilate. And trying to keep moving kind of quickly so we have an opportunity for homework if we can get there. We answered those. If you guys want to test this out, by the way, there is an e-tool, but I just decided today we would not use Chromebooks, especially because these somewhat shorten the classes. I'm going to go ahead and just let you guys start your homework and start playing with these situations and experiment with it.
I like playing with things.
So in these situations, please carefully follow their directions. You may work together. And this stuff, guys, is going to relate with what you're doing in science right now. How you've been working with, like, graphing lines and things like that.
So I see you talking to Dilo.
Yeah, exactly. Yeah, you already went to science and did some of that. So you have like 5-ish minutes before we release you early. And I'll just go ahead and leave these up here, so you don't even have to get a book out or anything. You can just look up here for these questions.
Do we need the colored pencils?
Yeah, put your colored pencils away, please. I appreciate that you asked that.